All right, so in the last video we talked about the idea of ionization energy, and we said that when you add an electron, you remove an electron. Well, when you remove an electron, now there are more protons than electrons. There are more positive charges than negative charges, which means then that this overall particle has gone from being neutral to being a positively charged ion, and we call those cations. Okay? Now, when we talked about elements on the left side, okay, we said ionization energy increases this way. That means it obviously decreases that way. Okay, so it's easier to take electrons from the elements on the left side than the right side. Well, if you go back to the videos that we talked about with ions that you're supposed to know from the summer, you'll know that the elements on this side of the chart do tend to be positively charged, and that's because, again, they have low ionization energies. Okay, so they give off electrons easily, and so they form cations. Okay, so obviously the reverse has to be true then. Okay, if the elements on the left have low ionization energies and form cations, and the elements on the right have high ionization energies, and so they tend to form anions instead. Okay, because it's so hard to take an electron from these elements, it's easier for them to gain an electron, okay? And when they gain an electron, now they have more electrons than protons. They have more negatives than positives, so overall they are negatively charged, and we call those anions, okay? So if you remember from the video that we talked about there, okay, the fluorine family, the halogens, they form -1 ions, fluoride, chloride, bromide, iodide. Okay, COM16, oxide, sulfide, selenide, telluride, okay, they're -2 ions. So the negative ions tend to be this way. But remember, the halogens are an exception there because they don't want to give or take electrons. They're noble. They're happy the way they are. They don't want to change at all. Okay, but we have to recognize that there are cations and there are anions. And this is what's going on, and it does relate to the idea of ionization energy. Now, yesterday, we talked about the idea that when you remove an electron, the size of an atom is going to decrease as it becomes an ion, okay? Because there are less electrons now, so there's less repulsions going on, okay? So every time we take an electron, it gets a little energy level, then it gets a lot smaller, okay? But either way, cations are always going to be smaller than the element that they were made from. So a sodium atom is bigger than a sodium ion, okay? A gold atom is bigger than a gold ion, okay? Well, then anions, again, have to be the reverse. If cations get smaller because we remove an electron, then adding an electron should make them bigger. And so anions, okay, as we add electrons, we're increasing the number of repulsions, which is going to make the atoms get slightly bigger the more electrons we add, okay? So anions tend to be larger than the atoms that they're formed from. So a fluoride ion is bigger than a fluorine atom. An oxide ion is bigger than an oxygen atom. Okay? So we have to, again, talk about that idea. So you see that represented here. But I want to relate it to the trend we were talking about the other day with atomic radius, okay, the size of atoms. The other day we talked about from left to right across the period, we expect the size to decrease, from top to bottom size to increase. Okay, let's just focus on the positive ions, the cations, the purple ones here. From left to right, we see it decreasing in all cases. From top to bottom, we see it increasing in all cases. Okay, now let's look at the nonmetals. From left to right, we see them decreasing in size. Not a lot in some cases, and there is an exception here. But yes, okay. Now from top to bottom, we see an increase going on, okay. So we see the basic idea, the same trend for atomic radius and ionic radius. The difference is when we talk about atomic radius, we can look at the whole chart, okay. When we talk about ionic radius, we have to just focus on just cations or just anions. Okay, you can't compare apples and oranges, okay? So we really can't make a comparison because notice from left to right, if we do the whole row, we go a little bit smaller, then jump up, and then go smaller again, Okay, and that would occur every time we switch from cations to anions. All right, so there are some exceptions there, but again, we're not worried about exceptions. Okay, so you should have a fair basic idea about ions, and so we want to talk about ionic bonds. Okay, well, we haven't used the word bond yet, not James. Okay, so what is a chemical bond? A chemical bond is just an electrical attraction. We've been talking about electrical attractions already, so we're still in the same vein. Okay, when we say that elements are bonded together, what we mean is that the nuclei of one is holding the electrons of another atom, and the nuclei of the other one is holding the electrons of the first one. So they go back and forth, and they hold each other kind of into place and lock in, and we call that a bond. Okay. So then what is an ionic bond? Well, an ionic bond is an electrical attraction between cations and anions, but how it's formed is a little different. Okay. So let's say we're going to take a sodium atom and a chlorine atom and put them together. Sodium has 1 valence electron, chlorine has 7 valence electrons. Okay, so sodium, being a metal all the way over there, has a low ionization energy. It doesn't care that much about that valence electron. It could come off pretty easily. Chlorine, on the other hand, all the way over this way, has a pretty high ionization energy. It wants to grab an electron. It doesn't want to lose one. So that's what they do. They just say, all right, I'll make you happy, you make me happy. Sodium loses the electron, chlorine gains the electron. Okay. Now, when sodium loses the electron, it becomes positively charged. When chlorine gains the electron, it becomes negatively charged. And now we have a positively charged cation, we have a negatively charged anion, and opposites attract. And now we have an ionic bond. Okay. So ionic bonds are formed when electrons are transferred, causing us to make cations and anions that attract one another. Okay. So that is the idea of an ionic bond. Okay. All right. So now, if we're talking about ionic bonds, we should talk about ionic compounds. Okay. There are different types of compounds, and there are different ways that each type of compound are named. We're going to talk about just the basic ones here of ionic compounds. Okay. The word nomenclature you see on the slide there has to do with a naming system. So we're going to just talk about naming of simple ionic compounds. Now, you know that NaCl, or maybe you know, probably know, NaCl is generally called sodium chloride. Why? Well, because in an ionic compound, all we do is name the cation, name the anion. Na is called sodium, Cl is called chloride. Boom, done. That's it. That's all there is to it. Okay? Nothing fancy about it. However, you got to keep in mind, as you see in the chart here, a little reminder that some of the elements have more than one possible ion, and that means that they have a Roman numeral associated with them. Okay? So, again, go back to the video about the ions that I had posted. It's on one of the previous slides. I linked it in. Okay? I'm not going to go into that now. But basically, your transitional metals tend to form multiple ions, so they have a Roman numeral to specify which one it is. Okay? So just to point out one, for example, here, look at chromium. I see Cr2 plus and Cr3 plus. Cr2 plus would be called chromium 2. Cr3 plus would be called chromium 3. Okay, the Roman numeral indicates the charge. Elements in group 1 and 2 don't get Roman numerals because these are always plus 1, these are always plus 2. And then we have a little diagonal line here of silver, zinc, aluminum. Silver is always 1, zinc is always 2, aluminum is always 3. Now, technically, cadmium is always 2 also. I'm not worried whether you remember that or not, okay? As long as you remember the 1, 2, 3, you could assume that all other metals get a Roman numeral, okay? Yeah, all right. Okay, so backing up to the idea of a compound again, okay? We need to understand that a compound is a pure substance, okay? When we talk about water, okay, we're talking about, even though it's more than one element, it's homogeneous. It's the same. So one drop of water, another drop of water, always going to be the same, assuming it's just pure water. Okay, carbon dioxide, a compound. Ammonia, a compound. Okay, hydrogen peroxide, a compound. Okay, compounds just mean that we have 2 or more elements that are held closely together through electrical attractions. Okay, now again, the ratios are very important. Notice in this one we have H2O. Now H2O we use for a lot of things in our life. Okay, eating, drinking, well, cooking I meant to say, drinking, bathing, okay? Hydrogen peroxide, not used in any nearly the same ways, okay? What's hydrogen peroxide used mostly as? We use it to clean wounds and whatnot, right? And when it gets in there, it kind of burns. Could you imagine showering and bathing in hydrogen peroxide? No, no, no. Okay, so the fact that it's one extra oxygen on there makes a huge difference in the behavior, okay? So please keep that in mind, and that's where the nomenclature thing is going to become an issue. We need to make sure we know which ones we're talking about when we look at formulas and or names. Okay, so we're going to talk briefly about binary ionic compounds. The term binary means two, okay? So just two elements. We're not going to get any fancier than that for now. We'll come back to larger ionic compounds in another unit. Okay, so now we're just talking about two elements. The first element is the cation. The second element is the anion. That's it. Okay, and again, you can go back to the video for help on the summer assignment. Not going to do that. You should know that the anions always end with the letters IDE. So a fluorine ion is called fluoride. A chlorine ion is called chloride. A bromine ion is called bromide. An oxygen ion is called oxide. A nitrogen ion is called nitride. All negative monatomic ions, monatomic meaning just one element, okay, one atom, okay, they all end with I. Okay, so carbon would form carbide, and so well, silicon would be silicide, but that doesn't really happen. But in any event, that's the idea. Okay, so keep those in mind as we talk about the nomenclature. Okay, so when we're naming ionic compounds, a couple things you need to remember. First off, the cation always comes before the anion. It's always positive ion, negative ion. It's important to note that to be a compound, it can't have a charge. If it has a charge, we call it an ion. Okay, so the total charge of any compound must be 0. Okay, when we're naming them, we always name the cation and check to make sure if it gets a Roman numeral. And then we name the anion, make sure the ending is IDE. Okay, the number of ions does not affect the name. Okay, let's talk about that. Okay, so let's talk about MgCl2. There's 2 Cl's, okay, as opposed to NaCl had the 1 Cl. Doesn't affect the name, okay? We're going to pull it out the same way. So Mg is magnesium. Now, first thing I do is I look at the periodic table and I see, does magnesium get a Roman numeral? No, it does not. So it's just magnesium. Okay. Then I look for Cl. Cl is chlorine, but I know the ending is going to be changed to chloride. So MgCl2 is just magnesium chloride. That's it. The 2 is there to balance the charge. That's all. Because the total charge of a compound has to be 0 to be a compound. Magnesium is always +2. Chlorides are always -1. So if I were just to put 1 magnesium and 1 chloride together, I would take a +2 charge and a -1. That doesn't equal 0. But if I take a +2 charge and take 2 -1s, now it does equal 0. Okay? So that's where subscripts come into play, is to make sure that the total charge is 0, to make it an actual compound. Compounds must be neutral. They have to have a charge of 0. Okay? All right, let's do another example. Ni3N2. Okay, so Ni, I look at it right over here on the table. Ni is nickel. Does nickel get a Roman numeral? Yes. How do we know what it is? We're going to have to figure it out. So we know it's nickel, and we know it's going to have a Roman numeral. Now we go on to the second part. So N over here is nitrogen. Now nitrogen, I know, has to be a -3 ion. Okay? And I know that the total charge of a compound has to be 0. Okay? So you'll see that I could say that, well, in this formula, we have 3 nickels, we have 2 nitrogens, and the total charge has to be 0. Now, I said a moment ago that nitrogens have to be -3. So I have 2 -3s giving me -6. I add 6 to both sides. I have 3 nickels and has to equal +6, which means nickel has to be +2, which means then I know the Roman numeral is 2. Okay, so it's nickel 2. Okay, and again, the nitrogen ion, we change the ending to "ide", so this compound would be called nickel 2 nitride. Okay, all right. Let's do one more example. Well, let's try a couple. So we have Al2S3, SbF5, BaSe, Ag3P, TiO2. Feel free to pause the video and give it a try, but I'm going to go on. So Al2S3, Al is aluminum, S is sulfide. Aluminum does not get a Roman numeral. Done. Sp is antimony, F is fluoride. Antimony does get a Roman numeral. Now fluorides are -1 and there's 5 of them. So 5 -1s means that this has to be +5 or Roman numeral V. Ba is barium, Se is selenium, but we changed it to selenide. So does barium get a Roman numeral? No, so it's just barium selenide. Ag is silver, P is phosphorus or phosphide. Okay, does silver get a Roman numeral? No, it's one of the ones on that diagonal line that does not get a Roman numeral. So it's silver phosphide. And finally, we have Ti, which is titanium, O, which is oxygen or oxide. Does Ti get a Roman numeral? Yes, it does. Now, I know oxides are -2. I have 2 of them, so 2 times -2 is -4, which means that titanium must be +4. It's titanium 4 oxide. All right, should be able to try some of these on your own, and I'm always willing to discuss it further with you individually. All right, let's get to it.